All right, so my name is Corey Nalgis, and my senior project design for the OE capstone was the design of a depth keeping AUV. So my main motivations for picking a project was to learn new skills, mainly electrical design, system integration, software design, and project management. And I've always had a lot of interest into underwater robots, particularly ROVs, and I really wanted to try and incorporate that. So my first selection was an ROV with a robotic arm, but to do that in a year is rather difficult. So I scaled back. I looked at maybe reducing some motor count and trying to eliminate those types of complications. And then I started looking at, well, what if it just hovered? What if it was much more like an aerial drone for underwater? It's still a fluid at the end of the day. So that kind of dictated a lot of my thought process. So what is an AUV, an autonomous underwater vehicle? So the ROV manual classifies AUVs as any unmanned underwater vehicle without a direct tether to the surface, used for underwater seafloor mapping, data collection, and general observation. And the image on the left is a bit more of a traditional AUV. It's much more streamlined. It's for long tracks where the control surfaces do a lot of the positioning, along with a forward-facing propeller. And the one on the right is a bit more unorthodox. It has tilting control surfaces for positioning. It can hover. It can do a lot of other things. So AUV is a blanket term for a lot of different classifications of vehicles. So for my goals, I wanted to design an AUV that can locate a depth, position at that depth, and then hold that depth within plus minus 5 centimeters, And the reason I chose plus minus 5 centimeters was I'm never going to have this out as an actual thing. It's a prototype. So testing in a pool was much more realistic, 1 to 2 meter depths. And for the budget I really had, plus minus 5 centimeters seemed like an adequate goal to find a pressure sensor that could realistically keep that accuracy. And I wanted this to be a proof of concept for a hovering AUV, more like that drone style that I was speaking about before. And for aspirational goals, it would have been awesome for it to 3D traverse, essentially like a drone flying underwater. So all AUVs have a bunch of different systems. For my AUV, I classified 4 main subsystems. So the control subsystem, propulsion and actuation, or actuation sensors, and the housing. So for control, I used an ESP32 microcontroller. For propulsion, I used brushless thrusters. Here's 2 examples that I planned on using either of them, and electronic speed controllers to control those. For sensors, I chose RO2 pressure sensor. It's the same pressure sensor used in the MAR 431 class. So a lot of students already have experience with it. And then I used the B&O 9-axis IMU. It's this blue chip for my orientation sensing. And for the housing, I used an acrylic tube and 3D prints. So for the propulsion system, I was originally donated 3 Blue Robotics thrusters, the large black ones. They're very heavy, they're very powerful. I actually have a graph with how strong they are later. The problem with the 3 is the kinematics are very complicated. They require accurate angle detection, and it doesn't give you a lot of control in the yaw direction, that is rotation around the vertical, because you have an angular momentum that's not being canceled out by one of the thrusters. With 4, it's a lot simpler. You have 2 axes, and the angular momentum's canceled there. And even though I switched from 3 thrusters to 4 thrusters, I actually lost weight. So 3 T100s is 900 grams. The RC boat thrusters that I eventually used were less than 750 grams. So here's my electrical schematic, so I'm going to walk through it. So I chose an 11.1 voltage battery, 3-cell 1P. It goes to a power distribution board. From that, it breaks off to the 4 ESCs. This schematic includes 3. And from those ESCs, they power the motors. Backtracking to the distribution board, I used a 5-volt regulator to step down the power. Going to the ESP32, it accepts around 5 volts because it's generally based on USB. And then from there, all of the logic coming off of the ESP32 is 3.3 volt, going to the IMU, the pressure sensor, and then PWM for the ESCs. So what is PWM? Pulse width modulation. It's the way you can use an analog signal to control really a lot of devices. In my case, the ESCs, the electronic speed controllers. So it's an analog signal to vary output. Standard speed controller's period is 20 milliseconds, and the way it controls it is you can actually kind of see it here. It's very small. Sorry about that. It varies how long the voltage is on to create an average voltage going to the controller. And 1.5 milliseconds is usually the neutral for bidirectional ESCs, meaning they're not getting any voltage sent to the thruster. So it's holding position. And then you vary this up or down. So this is actually the graph for the T100 thruster. So this is in kilograms of force. Full forward's about 3.5 kilograms. And once you multiply that by 3, you have a lot of thrust underwater. So controlling the AUV, I used a PID loop. This was essentially to control how I reach my depth target, how I reach my keep my angle steady on pitch and roll. So pitch and roll are the XY rotational elements for a 3D object. So a PID controller is essentially a feedback-based loop where you set a set point, then you measure the error from that set point, and then you apply 3 terms. So the P term is a proportional term. It works to vary the farther you are away from the target, the faster the P term is, the less so it slows down towards the target. I, so the longer you are away from the target, it takes the integral and keeps adding so you don't run out of time, or you don't slowly approach. And then the D term is a derivative, so you actually measure how fast you approach the target, so you are slowing down with another term. And then you add these all together to a control value, and then you run that into your process. And that actually applies continuously. So I actually wrote my own PID controller, and this will be posted to the USM Ocean Engineering GitHub if you want to look through it. But essentially, I called the same PID controller for all 3 of my loops, one for depth, one for my roll angle alpha, or one for my pitch angle alpha, one for my roll angle beta. And the way, I mentioned this before, but the kinematics kind of did simplify with going to 4 thrusters. So essentially, because this is a depth-facing PID loop dominantly, I'm always trying to have a positive UZ velocity in the down to reach my target. And then from there, if I roll along alpha, my pitch angle, I just have to vary thrust to correct it, which is why X1 and X2 apply the alpha control process inversely. One adds and one subtracts. Same thing with Y1 and Y2. So if they're tilted in towards an angle, a positive angle, one minuses, one adds to keep the thrust the same. So we're approaching the target at all times. For my housing, I chose the acrylic tube for the main housing. It's inexpensive, it's easy to cut, and it's very clear. And the 3D printed material I chose was PETG. It's commonly found in water bottles. It's very durable, and it's easily painted for waterproofing. So for my main housing design, I went 2 directions at first. My first iteration was very low profile, wide, wasn't very efficient for space. So the second one was much more efficient, being extremely streamlined in the vertical. And this also gave it a lot of stability in water. So it would right itself if something happened without a lot of need from the thrusters, but still fairly space inefficient, and it wasn't really what I wanted. So for the new iterations, 3 and 4 went together. They're very, very archetypally the same. Low profile, 3 thrusters. And then I actually had this ring for the thruster mounts on 4. The base cap was a bit more finished. And then I did the first set of O-ring seals in the top caps for 3 and 4. So version 5 built on 3 and 4 very heavily. It's a much more serviceable design. using dovetails for the thruster mount, so they quick disconnect if something breaks or a design change needs to happen. And then the electronics cage was much more open. This allowed for easier viewing, easier cable routing. And then version 6 was primarily the transition to 4 thrusters. So this added a pressure sensor mount to the base cap. It was taller to try and accommodate all the electronics, adding another electronic speed controller, and then another set of thruster wires. And then I actually added the cutouts for these waterproof connectors so they glue into these slots in order to get power to the ESCs. So for my O-ring design, I originally didn't really understand how O-rings worked. I just made it the dimensions of the O-ring, sealed it to the part. That didn't seal properly. So then I went to the Parker O-ring handbook, found the interior diameter of my acrylic tube, then used all the parameters to make a cap. Worked perfectly then. So this is actually all in millimeters. And then my electronics cage, much more open than the crosshatched electronics cage. The ESCs mount on these walls. And then even with that, it's very, very tight in the actual models. So you can see the 4 ESCs here, the power distribution board here, and then everything goes down with trying to keep all the wires and everything out of the way for the battery at the very bottom. So for the base cap, it's where everything comes together. So I actually inset the battery into the cap to lower the COG for stability as much as I could. And then a cutout for the pressure sensor, mounts for the IMU, and then mounts for all the thruster mounts. And now this was really tricky. So for my pressure sensor mount, it was very difficult because the Baro 2 pressure sensor I picked was only about 3 millimeters across. And this is very, very hard to mount to. And I was originally just using a standalone board mount one. I then switched to one mounted on a board, dictated in blue or notated in blue. And it interfaces with this gray aluminum plate via its O-ring. And then a 3D printed piece glues on top of the aluminum plate, and then a 3D printed pusher bar holds it down. And it's very difficult to see, but this little circle is the corner of the pressure sensor. The pusher bar pushes right behind the O-ring. So for the results, I designed a fully functional AUV from the ground up with the ability to depth keep and orient underwater. I conducted multiple elevator tests to see how pressure and the gyros or the IMU were able to correct and change throttle for the thrusters. Although due to space constraints, it's not realistic to seal the full AUV, so because there's not enough space for the wires to sit comfortably. And then theoretically, though, with the elevator test, it shouldn't have any problem achieving the accuracy underwater, but there's just no way to do the test in the time remaining. So, in conclusion, I set out to accomplish some goals about learning, and so I learned how to design and select electronics that work together. I learned how to design a PID controller from the ground up. I learned how to integrate systems, specifically the IMU pressure sensor working together with code in real time. And then the biggest one for me is I didn't really know how to work inside a spherical object. And that's very, very common for underwater vessels. And then, so learning how to design within that area was really a huge part of it. And then I learned how to design O-ring seals and design for waterproofing. Thank you. Questions?
So did they get around to testing it in full?
No.
Do you believe though that it works?
With some tuning, yes. So I don't have any tuned PID values, but just moving it up in the elevator, so it doesn't have a lot of relative accuracy underwater, or in air, has all its accuracy underwater because it's a denser fluid. We were seeing a lot of change just going up and down the elevator with higher PID values, so I have full confidence with a couple hours of testing and tuning.
So for the pressure sensor itself, is it completely inside the capsule, or is there a little plate that goes outside?
So there's this cutout in the bottom of the base cap, and glued into that is this plate with this 3D printed part on top of it. And that actually glues into a hole directly in the base cap. So O-ring seals to the aluminum, and the aluminum is glued down to the 3D printed part.
So the wire itself pushes onto that sensor?
Yes. And so the only thing in that hole is the sensor, the O-ring, and the edges of the aluminum plate.
As a student that is taking the first part of senior projects in design, or like somebody who's already finishing senior projects in design, what would your, what do you call this? What is that called? Like something that you tell somebody? Advice. So, what is your advice for the students that are taking the first part of senior projects in design?
I would just keep everything written down perpetually. When you have an idea, write it down. That's my biggest advice. There'd be so many times where I was backtracking, trying to figure out what I thought of before. That, and it's okay to simplify. If you're slowing down and something's stopping you, try and simplify it, or either move around it slightly, but don't ignore it.
That's second best. Good documentation is very important.
It's the best documentation I have.
Do those thrusters, do they turn sideways, or are they just stuck vertical?
They're fixed vertical.
Okay.
Yeah. Early on, I thought about having them tilt with servos. Overcomplicated, and you don't really need it.
Yeah.
Drones don't need it in air. If you're dealing with a denser fluid, you can move a bit more controlled. It is why ROVs don't really need vectored thrust.
So say it's same concentration and you've got some current that's pulling it away. Is it just going to go with current and keep it level, or is it going to fight current with the value?
If the current changes the angle, it would account. If it moved it just laterally without changing angle, it would not change.
Okay, so
Yeah, if I got to the 3D traversal part, that was going to be a part. You had a question?
Yeah, if it was control, like if you were manually controlling the side or something, being in a denser fluid, you probably would turn it sideways.
Yes.
Launch it forward.
Yeah, it works how an ROV works. Right. Like ROVs don't have a lot of combination thrust. They have set thrust in every axis. So I can go to the picture of one. So this one probably has 2 or 3 forward or vertical thrusters, and then a couple pointed each direction. With this, it's going to change the dynamics moving around in 3D, but it's not going to struggle.
do you have more power pushing up on your thrusters or down on thrusters? Which way are they tilted?
What do you mean?
So you said it was from an RC boat, right?
Yes.
Okay. Most of the times on the propeller, you've got more thrust going forward than back. Which one's the forward in this case?
I'm not sure. I believe it's counter to how boat propellers work. So for boat propellers, the nose of the propeller points back. I think on these, because the pitch is a little different, down is going to be the strongest. But I'd have to check.
I actually think the little discussion we had the other day about non-symmetric thrust curve.
Yes.
You go through the picture.
Yes, I was going to talk to you about that today because I did the same research. So my prior understanding was brushless motors were biased a direction, but this is actually the case with brushless motors. I think it's called the armature or brushed motors, the armature effect. It has to do with the axes on the magnets and how they're biased by the direction of the spinning motor. But brushless motors don't really have this.
I think it's just geometry.
Yeah, I think it's the propeller.
One direction is more efficient than the other. And that's kind of efficient.
Yes.
Are you ready to cast? Are you printed?
Yeah. What do you like? The base and the top?
Yeah.
Yes.
How did you seal those?
I painted them.
Okay.
So I just used spray paint. This is actually just clear coat at the top, and then this is an enamel spray paint. So I left the bottom submerged for about 2 hours, and I had no change in mass. And then I submerged the top cap with the O-ring in the acrylic, and then after 30 minutes it had no ingress of water. So I think it sealed pretty well. Your mileage may vary if you put it in the environment with chemicals in the water.
How are your thrusters attached to the vessel itself?
So I didn't show the updated version because it's quite a bit like the prior version. So do you know what a dovetail is? So it's a common woodworking joinery where you have two trapezoids into a negative of those two trapezoids, and it slides together, and then these screws pin it in place. It worked great for the lower profile motors because I had one big vertical going down. Because these are much taller, it was harder to get them to mount. So I actually have sideways ones, and the screw's not working great. It's there, but the pressure I can put down into the plastic isn't great. So if I was going to redesign everything, I would actually set the main dovetail into the base cap and then pin it in place there, which would lower the thrusters even more and add a lot more force that I can apply to them. And that's actually why this is strung up like it is, that they're warping under the pressure or under the force. This design, the bottom of the motor was actually on the floor, so it wouldn't really have that cantilevered force. These kind of forced me to go up a bit. So you could either inset it into the base cap, or you could add more mounting points, spread the force out further.
The screws that are in a dovetail, is that just threaded into plastic, or do you have threaded inserts?
It's threaded into plastic. There's threaded inserts everywhere else. Due to the nature of how 3D printers work and the shrinkages, getting a heat set insert into a dovetail was fairly difficult. That was originally the goal and the idea, but just threading into plastic works. There's heat set inserts everywhere else on it. So where the IMU mounts, the pusher bar for the pressure sensor, and then where all four thruster mounts. And they're just M3 heat set inserts.
Is it neutrally buoyant, or is it?
It's positively buoyant. It will float. Yeah, in total with the battery, it's 4 pounds. I don't have the exact number for how much water it displaces. It's quite a bit, especially if I went with a taller tube like in the final CAD design. The idea was to adjust this. So I had a buoyancy adjustment in the tube, and then I can always add more weight. So I had adjustments on both sides. But for most applications, you want it slightly positive. So if it turns off and you have no control over it, it floats to the surface.
You said those wires that were exposed right there. I'm guessing it's a marine grade connection. So that's every round.
These. So actually, in the actual connector, there's a gasket, and then the inside of this is sealed with silicon. So I believe they're automotive connectors, and they're supposed to seal in the engine bay. That's why I dammed up the back with silicon. Because one of the major concerns was water leaking through the wires, because I'm using stranded cable everywhere. So
you did the silicone job?
yes. But there are small rubber gaskets where each of the wires go in. They're just very, very dainty.
Have you tested the water?
Yes, when I did the submersion test with this, these were plugged in, no egress. And for the outside, I'm not worried about water getting in the outside of the connectors because it's not conductive enough. It's not going to short low voltage, low current like that.
Have you used any kind of standard or codes in your design?
So one of the main standards was the O-ring design, and then PWM was also a standard, and then it's a little bit unorthodox, but I2C. All of my sensors function on that bus, so those are my three standards. Mechanically, this is the main one. The others are protocols that you don't think of as standards originally, but they are.
Your connections rated by IP?
I don't believe so.
Ingress. Like IP67?
No.
If they are from automated, we should.
I don't think they have the certifications for that.
And what are the constraints of your design?
So one of my major constraints early on was I was donated those three thrusters. So the T100s or the T200s, which are the upgraded version that they're the only ones you can buy now, are about 200 each. So I actually designed around, and I selected the housing to accommodate an ESP and 3 motor controllers or 3 speed controllers. And then that's how everything came to be. So when I switched to 4, I gained a lot of volume inside that I wasn't expecting. And that's why I got to the point where it couldn't seal. One of the, if I could do it differently, I would actually board mount all of the electronics to design a custom PCB to keep everything very tight. And then I probably would go with a custom battery solution if I could, using 1850 or 500 cells to keep the weight even lower. Because a lot of the inside of the enclosure is controlled by the battery, because the battery has to be in the center.
So if you could lift one of the constraints like money, time, more people to help you, more knowledge with yourself, what would it help you the most?
If I started today. Like if I started today on the project with what I know now, it would be done way sooner.
But you would need more money, you would need more foresight and experience.
More foresight, more experience. Money helps, but I mean, it's not the determining factor, I think.
So what would you do different then?
As I answered before, I would design a custom PCB, mount everything. I would go to 18500 cells, the rechargeable battery cells. Have a layer of those to keep the battery even lower. I would use a 4-in-1 ESC. They're common in drones. They have 4 speed controllers on one board. Then they're about that big. They're very, very small. So I could eliminate a lot of space there. And I'd probably use these motors again. They're relatively cheap. The mounting pattern's annoying, but for what they are, they're quite good at what they do.
How fast is design to build?
It's not. I know that's a crazy answer, but it's more of just controlling the output. because they're powerful motors. Even these are powerful, and they're not getting quite as much thrust as the Blue Robotics ones. I think those are up here. I mean, what is that? 13.5 kilograms of force underwater. That's absurd. The Blue Robotics thrusters are designed to go on the back of surfboards to move humans. So just having one of those do that. Putting 3 on here, we knew it was going to be fast.
Designed for cavitation.
So actually, that's part of what this map does. So there are PWM mapping in the software I use, Arduino IDE, but I can actually control the limits here, and I can also control how much each function contributes to, or how much each PID controller contributes to the overall thrust.
You giving it a name?
I don't like this thing. Yeah. If I had to name it, I would name it Gregory. Because, so you might have noticed in my camera at home, there's like something in the left frame. It's a skeleton from like a Halloween decoration. And that's my proverbial rubber ducky. So software engineers have a rubber ducky that they bounce ideas off of at their desk for ideas. So I talk to Gregory.
Okay.
You asked a weird question, so I gave you a weirder answer.
You bought those thrusters like that, correct? Like you did
Yes.
The outsides?
Yeah, you can get them on eBay, you can get them on Amazon. I think they're, 13 a motor or something like that? I think they're around that. Yeah. And I question how much they're waterproof, because I don't think they'd last for long. You can kind of see it. There's just some silicon caulk in the bottom of those where the wires connect to the thrusters. So
they're not potted, they're actually like with epoxy, they're built with silicone?
yeah, I think they are. But brushless motors just work underwater inherently for a little while. If you put them into still water, they'd actually run forever. It's actually the minerals and chemicals in the water that erodes the windings on the coils. So at one point, I was thinking of just getting little film canisters like these sea perch motors go in. I don't know how many people are familiar with those. And then putting a very, very small brushless motor in there, covering it in mineral oil and sealing it.
Sea perch, is that the high school?
High school, middle school.
Yeah.
The little PVC robots with the little cans with brushed motors in them. Those motors were actually one of my selections early on because they're very, very cheap. But they're brushed, so it's a bit harder to control them.
So you probably came across those underwater drones which then came to aerial vehicles that was like UAV. Pretty close to what it is.
Yeah. Yeah, I have. Yeah, if I had larger propellers with less pitch, and I probably cut some weight out in everywhere I could, it would probably fly. A lot of research labs around that do this type of stuff have started making aerial drones that can land in water and then submerge. There is a real application for them. Which, seeing that, kind of validated the opinion that a hovering AUV was a real thing.
Cool. Anybody else? Questions?
Corey, did you program it to shut itself off and come back to the surface?
No. No, never saw the need. Operating in a pool at the end of the day, something goes horribly wrong, I get to watch it go horribly wrong. If something goes slightly wrong, I can grab it and get it out of the water. Because at the end of the day, if you get water in the system, there's not a lot that can go right, except if it's a very, very minor leak. To the point that anything would stop working, it's probably messed up. And also my time, it'd be running for minutes.
Did you take the engineering safety and ethics classes?
The two professors at the back of the room. Hey, it's not going to hurt anyone. And it's positively buoyant. So it is recoverable, so it's not an environmental disaster.
Cool. Well, thank you.